Good day, everyone. So, in today's lesson, we'll be looking at pressure in fluid. At the end of the lesson, we'll be able to define what pressure is, the application of pressure, and as well as the calculation involved in pressure and the principle that guide it. So, let's dive into this. Now, what is pressure? We'll be hearing it: high blood pressure, you exert pressure on something. What exactly is pressure? So when you talk about pressure, you know that you're dealing with force. So we could say that pressure is the force acting per unit area perpendicular to a surface. Okay, you could see this hand now. This hand is exerting pressure on this object here. Now, it's exerting pressure in the sense that it's applying force on that particular area. So the force you exert on a particular area is what we call pressure. So it is by formula force over area. So pressure is what? Force per unit area. Okay, and the unit of pressure is Newton per meter squared or Pascal, which is sometimes is written as PA. So it's either you have it as PA is Pascal or Newton per meter squared. Be aware that Newton per meter squared can also be expressed in another form. Can also express this Newton per meter squared as Newton per meter is per minus 2. So the slash there has become the power of minus. Okay. And lastly, pressure is a scalar quantity, meaning that it has magnitude but no direction. But it also means that it can never be negative. Anything that is scalar can only be what? Positive. All right. So let's move on to the principle that guides pressure in a liquid. Now, imagine that you have a container that has a liquid in it. Now, if you exert pressure at one part of the container, let's say here, now the pressure goes round, and affect the whole liquid. What is Pascal principle stating? It says any change in pressure applied to an enclosed fluid at rest is transmitted undiminished in all directions throughout the fluid. What that principle is stating is that in an enclosed fluid like we see in this place, if you exert pressure at one corner, let's say you exert pressure 5 Pascal at this particular spot here, it says that 5 Pascal affects all the other part of the liquid without changing. So it will not reduce to 4, neither will it reduce to 1. So pressure is the same throughout in the liquid. That's what the principle is stating, that in an enclosed fluid at rest, the transmitted pressure is what is transmitted undiminished, it does not reduce. So where are the areas of application of this principle? In hydraulic press. In hydraulic press, when you use the hydraulic press is a machine for lifting up an object. Now when it look like something like this way, okay, in this form, like this. Okay. Now what we have here is the liquid. So you exert a little pressure here, and the object is here. So when you exert a little pressure at this point, okay, the pressure moves and goes here and then lifts up this object. All right. The car brake that we also use in our car makes use of this same Pascal principle of pressure being circulated in an enclosed liquid without diminishing. All right. Now, the formula for pressure in liquid is different from pressure in solid. Remember, we said earlier that by formula, pressure is force over area. This is when we are dealing with pressure in solid, like that object we saw the other time, the man placing hand. But when you have pressure in liquid, the formula of pressure is density times gravity. This is it here. Density, this times gravity, times acceleration to gravity times height. That's the formula for pressure in liquid. Okay, where the G there represents 9.8 meter per second squared, or sometimes it's approximated to 10. So sometimes you can approximate it to be what? 10 meter per second squared. Depending on what you are given. you are giving it as 9.8, you use 9.8. If you are giving it as 10, please, you go ahead to use it as 10. All right. Now let's now look at uh, the atmospheric pressure. Atmospheric pressure is actually caused by the weight of air above a point, and this pressure decreases with altitude. So the higher you go, the lesser atmospheric pressure. But the constant atmospheric pressure that we have is 760 millimeter of mercury. Sometimes it's written as 760 millimeter Hg, where the H represents mercury. So this is another unit of pressure that we use in terms of atmospheric pressure. You know, we say it could be a Pascal unit, it could also be Newton per meter square. But sometimes we can also express pressure as millimeter mercury because we use mercury to measure it. So at sea level, it is 1001,325 Pascal. But at atmosphere level, which requires atmospheric pressure, it is 760 millimeter of mercury. Okay. Now, what do we use to measure pressure? The instrument for measuring pressure is called barometer. Barometer is used to measure atmospheric pressure, and we use manometer to measure pressure difference. Basically, we use it to measure gas pressure. All right. So these are the two basic instruments for measuring pressure. Either you use simple barometer or you use a manometer for gas pressure or pressure differences. Now, aside from the hydraulic press where we applied Pascal principle uh, and then brake, we can also find application of atmospheric pressure in siphon. You know, siphon can be found in our toilet seater. That thing that you call the flusher, inside it you have a siphon in it. But if you cannot have access to that, you can also experiment siphon by doing this here. You know, the basic principle behind siphon is that it's a U shape. It's a U shape tool that helps in transferring liquid from a higher to a lower level. All right. For this liquid to move from this point into this point, okay, the rule state that the pipe here has to be lower. Okay, it has to be lower than the pipe here. So for the liquid to move, and then the pipe here has to be inside. This one has to be inside, so that that means the water level has to be up to this place. Okay, and the pipe has to be here. So for siphon to work very well, there must be higher part of it and the lower part of it. The lower part of it is the one where the liquid goes, while the higher part of it is where the liquid is taken from. It is working because of the principle of the higher the pressure, the higher the height, the lower the pressure. Okay, so whenever the pipe goes lower, the pressure goes from the higher part. Okay, because pressure increases with decrease with height. So when the height is reduced downward, then we have higher pressure at this other side. So siphon in a nutshell look like this, something of U shape. So liquid goes from the higher part to the lower part because pressure goes from a place of low pressure to a place of higher pressure based on the height. We can also apply atmospheric pressure in syringe and in pump. The way pump works too is with what atmospheric pressure. The pump has to be positioned in a way that the the pipe or the hose inside it have to be in this U shape where the one side will be longer than the other, and the longer side is where the liquid goes into, because that's where you have the effect of atmospheric pressure being higher. All right. So I won't say that we will now do some of one or two calculations in this pressure topic. But before, let's see one question here. He said the principle of the transmissibility of pressure in a fluid at rest in all directions is known as a Archimedes principle. No, Archimedes principle is more for uh, then insertion of object in a liquid. So it's for when you are inserting object in liquid. It's more for flotation principle. All right. So it does not apply. Flotation principle, no. Archimedes principle give birth to a flotation principle. So this one is not deal with pressure at all. It deals with density and relative density. Newton's law, no. Newton's law, we all know this with motion. Pascal law, yes. Pascal law is correct one. Pascal law deals with what? Transmission of what? Transmission of pressure. Boyle's law deals with gas law. So the correct option is D. Okay, because it deals with what? Transmission of pressure. All right, let's see another question here. It says the arch door of a submarine had an area of 0.5 meters squared. Okay, so let's say that the area, let's split our page into two. So let's say the area given is 0.5 meters squared. Let's write our parameters out. The specific gravity of seawater is 1.03. Like we learned in our last lesson, another word for specific gravity is called relative density. So in other words, relative density of seawater, let's say RD, is 1.03. It is dimensionless, it doesn't have units. Okay, assume that G is 10 meter per second square. Now you see, now in this case, G is given as 10 meter per second square. So do not use 9.8 when you are giving 10 in the question. Whatever you are given is what you use. So in this question now, we are giving G to be 10. That is our acceleration to the gravity is 10 meter per second squared. And we are to neglect the atmospheric pressure. Okay, so now that we are neglecting the atmospheric pressure, so the force exerted by the seawater on the arch door at the depth of 200 meters. So we are given depth also, which is synonymous to height. The height of 200 meters is A 1.0 1.0 is power 3 times 10 to the power 5 Newton. B 1.0 is power 3 times 10 to the power 4 Newton per meter square. C 1.0 is the power 6 times 10 to the power 5 Newton per meter square. D 2.0 is the power 6 times 10 to the power 6 Newton. And E 1.0 is the power 3 times 10 to the power 3 times 10 to the power 3 Newton. Now we have to find the force. That's the question. The force exerted by the sea water on the arch door at the depth of this is what? So we're looking for F, the force. Now F is unknown. F is unknown. The force is unknown here. So how do we get that? So if going through the option alone, you know the unit of force is Newton. So if you have Newton per meter square as an option, you know that is off. It does not really apply. It does not really apply. So if you see it here, another in option C, you have Newton per meter square too. Of course, you know that the unit has disqualified this answer. So the unit of force is Newton. So the option could be either A or D or E because they are in Newton. But then we need to calculate it. Now let's look at the question now. We have to find force, and we know that for us to get force, we need to first of all do some manipulation. How do we get force? Since we know that by formula, pressure is force over area, right? We have area, but we don't have pressure. So that means we need to get our pressure for us to get force. So this one can give us the answer to force. Once we have our pressure now, so how do we now get pressure now? Formula for pressure in a liquid is pressure is equal to density times acceleration velocity times height. We have G, we have H, but we are not given the density of the liquid. Okay, we are not given density of the seawater. How do we now get it? Remember that we are given relative density. Now, relative density by formula is equal to density of the water, that is seawater now, over density of water itself. That is formula for relative density of water. Now, relative density of the seawater is given to be 1.03. That means 1.03 equals to density of seawater we don't know, and that's what we need here. Okay, so let's call it the rho that what we're looking for over density of water is a constant, which is 1000. Okay, it's either 1000 kilogram per meter cube or 1 gram per centimeter cube. But we are making use of 1000 because in our in in the density of water, if you use 1000, it is 1000 kilogram per meter cube. So we have meter cube here. So since we have meter per second square, so we need to go with if you go with the second one, which is 1 gram per centimeter cube. This centimeter cube will not will be forced to convert it to meter cube, and we'll be forced to convert gram to kilogram, which will see lead us back to 1000 kilogram per meter cube. So it is better you use this because it has kilogram, which is what we need. Anytime you're making use of G, then your unit of mass must be in kilogram, unit of volume or area or meter or length must be in meters if it is length, or meter square if it is area, or meter cube. Our area is a meter square, and we have meter cube here. So you have to be careful. So one will be wrong to be used because we do not have our area to be centimeter square, so we can't use here. We cannot use this one. So this is the reason why we are using 1000. So here now is relative density is 1.03 over density of salt of seawater over density of water. So rho there, which is the density of seawater, will now be 1.03 times 1000. Okay, so when we do 1.03 times 1000, we should be having 1030, okay, as our density of seawater. So that will be equal to 1030. So we can now substitute into this place to get the pressure of the seawater. So pressure of the seawater is density times gravity times height, and density we have obtained it to be 1030, then times G, which is 10, remember is 10, and times the height, which is the depth here, that's 200. Okay, so in other words, we have 1030 times 2000. Okay, 1030 times 2000, that will be giving us 2060. That will give us 2,060,000. So this amount to 2,060,000. Okay, so we have it as 2 million. Okay, as 2,060,000. Okay, so 2,060,000. Let's call it Pascal. Now, but we have to find force. So making use of this and making our F the subject of the formula, F there will be equal to P times A. Okay, and from there, multiplying it, that will be 2,060,000 times our A. Remember, our A is 0.5 times 0.5. So going back to our result from the calculator, 2,060,000 times 0.5. So we'll be having it as 1,030,000. Okay, so that will be equal to 1,030,000. Okay, so 1,030,000 Newton. And if you're going to express it in standard form, you'll be having 1.03 times 10 raised to power 6 Newton. Yes, so in standard form, it's 1.03 times 10 to the power 6 Newton. Let's go back to the option we have. We have said the one with Newton are the one that will likely be the correct one. So we have 1.0 to the power 3 times 10 to the power 5 Newton. That is wrong. We have 2.0 to the power 6 times 10 to the power 6 Newton. It's also wrong. Then we have 1.0. We have 1.03 1.0 to the power 3 times 10 to the power 3 Newton. That's wrong. Now the one with e to the power 6 is the correct answer. So that's 1.03 times 10 to the power 6. So option A is not correct. Option B is not correct because of the units alone. Option C is not correct as well. Okay, then option D is not correct. Then so none of the option is close to the answer. Maybe there is a typographical error there. So but correct answer is 1.03 times 10 to the power 6 Newton. All right. So we'll be ending the class here today. I hope you have been able to learn something from this topic. Thank you for watching and bye for now.